Okay, so what is a zero rate? Well, zero rates are the rates you would actually see on the yield curve. And a zero rate is the rate of interest earned on an investment that starts today and lasts for N years. So all the interest and principal is realized at the end of the period. So at the end of a half a year, the rate continuously compounded would be a 5%. At the end of 1 year, it would be 5.8%. So these are at the end of 1.5 years would be 6.4%. And at the end of 2 years, it would be 6.8%. So there's no intermediate payments. There's no payments happening in between. So these are actually what we would call the spot rates. If we went out a half a year, that's what the spot would look like. And we could plot this on a curve, and I did that by inserting a curve and highlighting these, and I created a chart. And I can name it, but I didn't do anything fancier than that. But that's what the curve would look like. I get a yield curve, right? The zero rate is a function of maturity, and it's referred to as the zero curve. So suppose a 5-year rate with continuous compounding is quoted at 5% per year. So say we went out 5 years. What would $100 mean invested for that long? We would have to take the exponent times 0.05 times 5, and it would equal 128.40, because that's what you would get at the end of 5 years. The forward rate is the future zero rate implied by today's zero rate. So the forward rate for a period between 6 months and 1 year would be 6.6%. That's because 5% for the first 6 months combined with 6.6% for the next 6 months would give you an average of 5.8%. Okay, so that's how that would work. That's how that would work. But this is this is another example. But let's take a look at an actual example that we look at from how to take these rates and turn them into. So if I know those are my rates and I know the term of my bond, so I'm looking for a 2-year bond providing a 6% coupon paid semi-annually, and I plug this into my formula, 3 to the exponent of minus 0.05 times a half, which would be up here. And then I get another, because this is a semi-annual payment, so the $6,000 face value of a bond would pay bond interest of $30 every 6 months. The second period would be 3, Euler's number or exponent, minus 0.058 times 1. Then the third would be 3 and 0.06 minus 0.06, because we're discounting these. And then finally I get the last payment of 3 plus my principal amount of 1,000, but these are expressed in percentages of 1,000. Like you know how bonds are expressed. So it would be 103 times minus 0.068 multiplied by 2 periods now, because we're discounting back by 2 periods, like I showed you in my discounting calculations or my discounting videos, and you're going to get 98.39. So now we know what the price of a 2-year bond using the theoretical zero rates at 6% would be worth today, 98.39. So the next thing I'd like to know is how do I find first the semi-annual payment. Now you could use this equation, or you can make it easy and you could just use Excel. So if I go to Excel and I plug in the 4 periods, the payment would be 3, which is the 3. The present value, now that I know, is 98.39. Now I have that number, that's what I'm paying today. And 100 or 1,000 would be what I get at the end. When I plug those numbers in, I'm going to get a semi-annual yield of 3.438%. If I multiply by 2, I'm going to get a 6.88% yield using semi-annual compounding. But now I want to know what that number is going to look like on an continuously compounded basis, and I would use this formula. It would be the periods times the log normal component, which is the opposite of Euler's number, which is the log of Euler's number, multiplied by 1 plus the rate divided by the periods. So in this case, I would get 2 times the log of 1 plus 6.88% divided by 2, since I'm dealing with 2 periods. And that's what I did here, and I get 6.88%. So this would be the semi-annual yield. This would be the actual continuously compounding yield of a 2-year 6% bond paid semi-annual using the zero rate spot rates. Now, if I want to just look at one more example, like do this on an annual basis, let's say this was an annual bond. Well, there would be no 3% payments. There would be 1 6% payment at the end of year 1 and 1 6% payment plus my principal at the end of year 2. So I would just be dealing with 5.8% and 6.8%. So 6 times exponent times minus 0.058, I don't need to multiply by 1 because it is 1, it's 5.66, I've discounted that back. Then I take my latest payment, 106 times that, multiplied by 2 now because it's the second period, and I get 92.5213. When I add these together, that would be my bond price, 98.18, as opposed to 98.39 when I had a semi-annual payment. Right? I pay a little bit more because I'm getting my money back a little faster. Here I'm going to pay a little less because I'm getting my money back a little slower. Now, I take that 98.18, plug it into a yield to maturity calculator, which is just basically 2 periods, 6%, 98.18, and 100, and it'll be minus 98.18. Always remember to put the minus sign in. I'm going to get 7%. That would be the semi-annual yield. And then to convert, I just have to take the log of 1 plus the semi-annual. I don't have to do what I did here, which was 1 plus, which I had to multiply by 2 in all cases because it was a semi-annual yield. Here I only have to go with 1 period. So hopefully that's clear. Play it over a couple of times. The explanations are here. If you want to stop the video and look at the actual, some of the actual text, but that's how we do it, right? So remember this conversion log formula is going to be the periods times the log multiplied by 1 plus the rate divided by the number of periods. Okay, so if you have annual payments, well then you just have to multiply by 1 plus the rate times the log. If you have semi-annual payments, you're going to have to multiply 2 times and then divide that coupon by 2. Okay, thank you.